Okay, so here we now. Basically, what I'm going to do here is I'm going to give you in about a 50-minute lesson made up of a few slides here, and then do your pre-lab. In a 50-minute lesson, I am going to do about the middle week 4 through week 8 of Physics 210. All right, so we're going to do it all right here in a. We're going to talk about, first of all, you need to know what a force is. A force is how much an object pushes or pulls on another object. Okay. All right. So here you go. You got the weight of an object. The Earth exerts a gravitational force on the ball, and then the table. The floor extends a support force on the ball, which is the gravitational force is a fundamental force, and the support force is a non-fundamental force. In other words, the gravitational force will always be the gravitational force. There's a gravitational constant. There's an equation that fits for it, and it is a fundamental part of physics. Whereas the support forces change all the time. It may or may not be there at times and things like that, and it doesn't. And also with the fundamental force, with the support forces, the energy is not conserved, which is all I'm speaking very esoterically and kind of over. And I don't mean to talk over your head, but it is. I mean, that's just making sure that the physics is correct. All right, so weightlifting and work. All right, here's a prelude. Now, how do we do weightlifting and work? So if a weightlifter doing the snatch lifts 77 kilograms, 2.5 meters, how much work does he do? Okay, well, I'm going to show you. I'm going to get out of this right now, and I'm going to show you. I'm going to take this very problem, and I'm going to write it out as notes. Okay, so this will be the Lab 2 notes, and I'm going to try and write it neatly, and we will do it. I'm sorry, I keep kind of laughing because when I was getting this slide, I know I'm going off on a tangent here. When I was getting this slide ready, or this video, I was getting ready to do this one. I was uploading your first track onto YouTube, and of course there's Melissa McCarthy doing Sean Spicer, and I just had to watch that again. I mean, so there was 4 minutes of my day just kind of flushed, but I'm still laughing about it. Anyway, so let's take a look at so we're going to apply a force. We're going to lift something up. We're going to, force is equal to a mass times an acceleration. Okay, we're going to lift it 2.5 meters. And we're going to see how much work is done to do that. All right, so we're going to escape out of here. Now there's the answer, but I don't want you to look at it. Don't look at that. I want you to keep your eyes on me, on me. Okay, it's all about me here. All right, so let's go to the ladybug. Hopefully it'll come on. Come on now. Help a brother out. There we go. Lab 2 notes. We got that on there. So here we go. We're going to lift. I'm just going to draw this as a ball. This is our 77 kilograms just sitting here on the ground. And then we're going to lift it up 2.5 meters. Okay, where the height is equal to 2.5 meters. Okay, the work done is equal to the force times the distance. Well, how much force is required to lift this up here? Well, first of all, we've got to overcome gravity, which is accelerating downward. Gravity is equal to negative 9.8 meters per second squared, which we looked at in the first lab. We know that's acceleration due to gravity. This is what we have to overcome. And so we normally lift this at a constant acceleration. So we're lifting it at a positive 9.8 meters per second squared once we get it going, and then opposed to the negative 9.8 meters per squared. So it goes at a constant velocity as we raise it up. All right, and then we stop. And so there's all kinds of little things going on in those microseconds from when we get it started, from when we get it stopped. Those are impulse forces working, and we'll look at those maybe a little bit later. But I've got work is equal to force times distance. Now the force to get that thing up there is equal to the mass times the acceleration. Okay? All right, so we've got the mass times the acceleration times the distance is equal to the work to get it up there. Well, if we change this, the acceleration is the positive 9.8 meters per second squared. So in a shorthand way, we're just saying, okay, well, it's mg times h is the work to get that thing moved up there. Okay, that is what it is. So it's 77 times 9.8, was it 77 kilograms? I hope it was, times the height of 2.5 meters. And so you multiply all that out, and I've got to find my calculator, which is here on the floor somewhere. I found it. If any of you ever want to leave a place screaming, you can come visit me in my office, which is a complete nightmare to anybody who's a little bit OCD. 77 times 9.8 times 2.5 is the amount of work. That's 1,887, because I'm going to round it, 1,187 joules. That is the energy. We use joules. Okay? All right, so let's, in fact, I'm going to stop. Introduction of work and joules is what this track is going to be. All right, so I'm going to stop here because I've yacked long.